Here we're going to take a different kind of look at the last three kinematics equations that we've been using so much. We're going to try to figure out where exactly do they come from. Now the first one, the velocity, we know it basically comes from a line, and the second one represents a quadratic function, which is a parabola, which we sort of know from math class, but we want to look a little bit deeper and think, like, what's actually happening here? Where did these equations actually come from? How can we derive them? So the easiest way to do this is to look at a graph of velocity versus time. So let's say we had meters per second versus seconds, and we wanted to chart the path of an object. Let's say, whoops, I missed the mark there. Let's say we go up to 15 meters per second. We started at rest and we sped up for 7 seconds. Now, the hunch might be, well, if we want to find the position here, we can multiply velocity times time, and go 15 times 7, we end up with 105 meters. But is this right? Does that actually make sense? And it actually doesn't work because it's not a constant velocity of 15 meters per second. Really, the velocity is changing, or more accurately, we could say it's increasing, right? It's accelerating from rest up to a speed of 15 meters per second, and we know that actually the slope of this line is the acceleration, delta v over delta t. So, if that's true, what is the position? It turns out position is actually the area under the curve. Now, that means because it's actually a triangle, we can just take half of that 105 that we got before and realize that actually the displacement of our object would be 52.5 meters. Now, this is kind of a big jump to take, but what we have to recognize is that velocity time graphs, their area underneath their lines represent displacement. Now, there's a whole slew of reasons why this is, and without getting too technical, maybe we'll save that until we learn a little bit more about calculus, but it does make sense. If we look at, say, a constant speed of 20 and we go for 3 seconds, we should travel 60 meters, and that is the area of that rectangle. Meters per second times seconds, it leaves us with meters. So what if we were to combine those two, and maybe we started at an initial speed of v0 and we accelerate up to vf, which means what we have to do is kind of combine the rectangle case and the triangle case. If we look at that line again, we can see that's where that first equation really comes from. It's just the equation of a line, y equals mx plus b, where the slope is the acceleration. So if we want to find the displacement, we actually have to find this area, because really what we're doing is the product of the two axes. We can unit analysis and we can see it that way. And let's work with some different colors here. And we'll say, let's say in green our rectangle is that constant speed times t. It's the area, whereas the triangle we know is base times height divided by 2. So in blue there, our base is the time and our height is delta v, and we've got an area for the blue triangle. So if we want to find the displacement of this object over a time t, basically we just add that green rectangle to the blue triangle. And the last thing we can do is we can substitute, instead of delta v, we can replace it with a times t. We substitute in at instead of v, and we're left with our t squared term that we're so used to from our parabolic shape of that quadratic sort of projectile that we know from math. So the last one, third equation, is the one that doesn't have time in it. So once again, we're going to use some substitution with our first two equations to figure out where the third equation comes from. Now, we're going to work in a little bit different space here. I'm going to move things around, and we know we're going to work with that first equation combined with our second equation, or second and first, the order really doesn't matter. Basically what we're going to do is substitute an expression for t, which is v minus initial velocity over a. We're going to plug that in instead of time. And now we're going to get a little mathy here for a second and recall what we know about fractions and polynomials, and we'll have to expand out that bracket there with FOIL, and we can cancel out an a. And to deal with all these fractions now, essentially what we're going to do is figure out what's the lowest common denominator that all the fractions share, and it turns out it's actually going to be 2a. So what we can do is you can actually multiply both sides of the equation by 2a, and we can sort of get rid of those denominators. We'll show that in red here. On the previous line, we multiplied by 2a over 1. It's the lowest common denominator, or LCD. The last thing is just to collect like terms, sort of clean things up a little bit, do some rearranging, and we're left with the form of the equation we've become used to, which we could call our third kinematics equation there, at least in our list. So hopefully you find that a little bit helpful as we dig deeper into these equations.